Izzah Mazarah, and in this video, me and my group members are gonna talk about light emitting diode. So, what is light emitting diode, or short for LED? It is a two-lead semiconductor light source. In 1962, Nick Holonyak has came up with an idea of light emitting diode, and he was working for the General Electric Company. The LED is a special type of diode, and they have similar electrical characteristics of a PN junction diode. Hence, the LED allows the flow of current in the forward direction and blocks the current in the reverse direction. The LED occupies the small area which is less than the 1 mm per square. The applications of LEDs used to make various electrical and electronic projects. The light emitting diode is a PN junction diode. It is a specially doped diode and made out of a special type of semiconductors. When the light emits in the forward bias, then it is called as a light emitting diode. So, how does the LED work? The light emitting diode simply we know as a diode. When the diode is forward biased, then the electrons and holes are moving fast across the junction and they are combining constantly, removing one another out. Soon after the electrons are moving from the N-type to the P-type silicons, it combines with the holes and then it disappears. Hence, it makes the complete atom and more stable, and it gives the little burst of energy in the form of a tiny packet or photon of light. From the diagram attached in this slide, we can observe that the N-type silicon is in red color and it contains the electrons. They are indicated by the black circles. The P-type silicon is in the blue color and it contains holes. They are indicated by the white circles. The power supply across the PN junction makes the diode forward bias and pushing the electrons from N-type to P-type. Pushing the holes in the opposite direction, electron and holes at the junction are combined. The photons are given off as the electrons and holes are recombined.
Hello, my name is Muhammad Aiman. This next slide, I will talk about type of light emitting diode. There are many types of LED, which is number one is gallium arsenide. This type of LED is used in the manufacture of devices such as infrared light emitting diode. Next, number two is gallium arsenide phosphide. This type of LED is used for manufacturing red, orange, and yellow LED. Number three is aluminium gallium arsenide phosphide. This type of LED is used in manufacture of LED of high brightness for red, orange, green, and yellow color to form the heterostructure emitting light. Number four is gallium phosphide. Gallium phosphide has been used in the manufacture of low cost in red, orange, and green LED with low to medium brightness. Next, number five is aluminium gallium phosphide. It is used to manufacture light emitting diode emitting green light. Number six is gallium nitride. This type of LED commonly used in blue light emitting diodes. Its wide band gap of 3.4 eV affords its special properties for application in optoelectronic, high power and high frequency devices. Next, number seven is gallium indium nitride. Indium gallium nitride is the light emitting layer in modern blue and green LED and often grown on a GaN buffer on a transparent substrate. Number 8 is silicon carbide. Silicon carbide is used in semiconductor electronics devices that operate at high temperature or high voltage. And lastly is zinc selenide. Zinc selenide is used to form light emitting diodes and diode lasers. It emits blue light. Next slide, I will explain about working principle of LED. The working principle of the light emitting diode is based on the quantum theory. The quantum theory says that when the electron comes down from the higher energy level to the lower energy level, then the energy emits from the photon energy is equal to the energy gap between these two energy levels. If the PN junction diode is in the forward bias, then the current flows through the diode. The flow of the current in the semiconductors is caused by the both flow of free electron in the opposite direction of current and flow of electrons in the direction of the current. Hence, there will be recombination due to the flow of these charge carriers. The recombination indicates that the electrons in the conduction band jump down to the valence band. When the electrons jump from one band to another band, The electrons will emit the electromagnetic energy in the form of photons, and the photon energy is equal to the forbidden energy gap. For an example, let us consider the quantum theory. The energy of the photon is the product of both Planck constant and frequency of electromagnetic radiation. The mathematical equation is shown EQ equals hf, where h is known as a Planck constant and the velocity of electromagnetic radiation is equal to the speed of light. The frequency radiation is related to the velocity of light as a f equals c over lambda. Lambda is denoted as a wavelength of an electromagnetic radiation, and the above equation will become as a EQ equals he over lambda. From the above equation, we can say that the wavelength of electromagnetic radiation is inversely proportional to the forbidden gap. In general, silicon, germanium semiconductor, this forbidden energy gap is between the conduction and valence bands are such that the total radiation of electromagnetic wave during recombination is in the form of the infrared radiation. We can't see the wavelength of infrared because they are out of our visible range. The infrared radiation is said to be as a heat because the silicon and the germanium semiconductors are not direct gap. Semiconductors, rather, these are indirect gap semiconductors. But in the direct gap semiconductors, the maximum energy level of the valence band and minimum energy level of conduction band does not occur at the same moment of electrons. Therefore, during the recombination of electrons and holes are a migration of electrons from the conduction band to valence band, the momentum of electron band will be changed.
Hi, my name is Siam Nicholas. I'm here to present you a 3-point LED, which are characteristic, application, and advantages of light-emitting diodes. For the first point is characteristic of light-emitting diodes. There are different types of LED are available in the market, and their different LED characteristics, which include the color light, wavelength radiation, and light intensity. The important characteristic of LED is color. In starting use of LED, there is the only red color. As the use of LED is increased with the help of the semiconductor process and doing the research on the new metal for LED, the different color will form. Next is the application of light-emitting diodes. There are many applications of LED, which are LED used as a bulb in homes and industry. Therefore, LED also used in the motorcycle and cars. Next, light-emitting diodes are used in the mobile phone to display the message. Last but not least, LED also used at the traffic light signal. Now, let's move to the next part, which I will tell you about the advantages of light-emitting diodes. First, the cost of light-emitting diodes is less and they are tiny. The second advantage is by using LED, the electricity is controlled. The last advantage is the intensity of the light-emitting diodes differ with the help of the semiconductor of the microcontroller.
Hi, I'm Irfan, and I'll explain about quantum dot-based light-emitting diodes, or QD-LEDs. It represents a form of light-emitting technology and are regarded like a next generation of display technology after the organic light-emitting diodes or OLED display. QD-LEDs are different from liquid crystal display LCDs, OLEDs, and plasma display due to the fact that QD-LEDs present an ideal blend of high brightness efficiency with long lifetime flexibility and a low processing cost of organic LEDs. So QD-LEDs show theoretical performance limits which surpass all other display technologies. The goal of this chapter is firstly to provide a historical perspective study of QD-LEDs, application in display and lighting technologies. Secondly, to present the most recent improvement in this field, and finally to discuss about some current direction in QD-LEDs, research that concentrate on the realization of the next generation display and high quality lighting with superior color gamut. The entire range of color available on a particular device, such as a monitor or a printer. A monitor which displays RGB signals typically has a greater color gamut than a printer which uses CMYK inks. When a color is out of the gamut, it cannot be properly converted to the target device. For an example, to a different type of printer, higher efficiency and higher color rendering index. QDs obeys the quantum mechanical principle of three-dimensional confinement of the charge carrier, that is electron, and holes that determine novel quantum phenomena and tunable optical properties, which are sensitive to the size, shape, and material composition of the QDs. QDs have an intrinsic energy bandgap that decides required wavelength of radiation absorption and emission spectra. The bandgap energy increase with decrease in dimension of the QD. The color of the light which a QD emits is directly connected to the size. Connected to the size. The bigger dots cause longer wavelength, lower frequency, and redder light, while the smallest dot produce shorter wavelength, higher frequencies, and bluer light. This dimension dependence permits the modulating of the bandgap energy by varying the size of the QD. QD technology is used to filter light from light-emitting diodes to backlit liquid crystal display. With the recent enhancement introduced by the usage of the QDs to backlighting technology, LED or LCD TVs are much better today than they were just a few years ago.
So for this part, I will explain about the structure of quantum dot-based light emitting diode. Due to the multiple advantage of using quantum dots, short for QD, and their application in optoelectronic instruments like LED, the scientists have created quantum dot-based light emitting diode, short for QD LED, with the improved efficiency and flexibility. QD LED represent the following generations display technology after an organic light emitting diode displays. QD LEDs are a form of light emitting technology for creating large area displays that could have application for TVs, cell phones, and digital camera. A classical QD LED is composed of three layers, one inner layer of QD as an emissive layer, one outer layer that transports electron, and one outer layer that transports holes. The researcher addressed this requirement by using a layer of 6 nanomicro cadmium selenide quantum dots and an electron transport layer made of zinc oxide nanocrystal. The researchers fabricate 4 different versions of QLED, each having different quantum dot film thickness, 15, 30, 45, or 60 nanomicro. After applying an electric field on the outside layers, electron and holes shift in the layer of QD, where they are captured by QD and recombine emitting photon. Due to the multiple advantage of using the colloidal QDs, the colloidal QDs are promising way for making QD LEDs. A great effect of an increased recombination efficiency is obtained by constructing an emissive layer in a single layer of QDs, so that the electron and hole may be moved directly from the surface of electron transport layer and hole transport layer. For the definition of the performance of QD LEDs is used the external quantum efficiency, short for EQE, which is the term that designs the number of photons emitted from the device per electron. QD LEDs not only reduce the consumption of energy but also show high color purity. Studies report the QD LEDs exhibit the ability to be more than twice as power efficient than organic light emitting diode as the same color purity. QD LED have an advantage of foldability and their wide application for next generation electronic displays and optical communication technology. QD LEDs exhibit pure and saturated emission colors with narrow bandwidth. In QD LEDs, the emission color is powerfully direct by the dimension of the used QD due to the confinement effects. It has been proven the QD LEDs present a 30 to 40% luminance efficiency advantage above organic light emitting diodes for the same color point. The color rendering index CRI indicating how accurate a given light source is, and rendering color when compared to a reference light source. The highest the CRI, the better than color rendering ability. Light sources with a CRI of 85 to 90 are considered good at color rendering. A color rendering index (CRI) is a quantitative measure of the ability of the light source to reveal the colors of various objects faithfully in comparison with an ideal of natural light source. Light sources with the high CRI are desirable in color critical applications such as neonatal care and art restoration. Advantage of using the technology, more realistic color and highest brightness, reduced power consumption, QLEDs display have longer product lifespan and less bandwidth, greater range of panel size.
As for the conclusion, we showed how the use of LEDs will allow us not only to investigate at a deeper level the phenomena with which we are already familiar, but also to discover and study the phenomena. We have constructed the following basic ideas relevant to LED physics. LEDs are small light sources embedded in a plastic dome and have an asymmetric I to V curve. They produce light of one color. Turn-on voltage of LED is related to the color it emits. Moreover, LEDs are composed of semiconductor materials and can either convert electric energy to light energy. That's all from us. Thank you for listening and paying attention.